Hey everyone, and welcome back to All About AI Tech. Today we're tackling a topic that's been shaking up the world of artificial intelligence, vision transformers, or ViTs for short. Now, I know what you guys might be thinking. Transformers. Aren't those things from NLP, from processing and understanding language? And you're absolutely right. The original transformer architecture was a game changer in natural language processing, handling complex text relationships with remarkable efficiency. But the brilliance of the transformer isn't limited to just words. Its core strength, the self-attention mechanism, is remarkably adaptable, and it has totally revolutionized the field of computer vision. The core mechanism is just the same: self-attention. This ingenious mechanism allows our models to focus simultaneously on several different parts in an image, irrespective of how far they are from one another. In this way, a ViT model can instantly learn the global relationship between various parts of an image, while simultaneously evaluating and extracting fine features, all from its very first layer. This contrasts sharply with traditional convolutional neural networks, or CNNs, where a high number of layers is needed in order to extract higher-level hierarchical representations. Think of it like this. CNNs are like meticulously building up understanding of an image one step at a time, starting with edges and textures and then working their way up in a piece-by-piece puzzle. ViTs are like having that sudden aha moment where you take in the entire picture at once. It's a fundamentally different way of looking at images, and it makes it possible to both speed up and improve accuracy of computer vision. Let's take a look at some of the recent applications of vision transformers. So why is the vision transformer so groundbreaking? This is the real power of the system. ViTs offer several crucial advantages over traditional convolutional neural networks. Firstly, ViTs are way more efficient at handling gigantic datasets. Imagine training a model on billions of images. That's what some of these models are doing, and their ability to handle this data at scale and still work effectively is nothing short of amazing. Secondly, ViTs are incredibly flexible and adaptable. Because they do not rely on local convolutional filters, they become more robust to noise. This means they can work effectively even with lower quality images that may be difficult to process for CNNs. This inherent resilience makes ViTs incredibly versatile for a wider range of applications and can work well using fewer training images. Thirdly, ViTs demonstrate much better generalization capabilities when pre-trained on large and diverse datasets, making it more efficient to retrain ViT models and significantly reducing fine-tuning times. This is remarkable when you consider how much effort and compute goes into building and fine-tuning traditional CNNs. Finally, ViTs are highly parallelizable, which means we can use the power of modern hardware, like GPUs, to make training and inference substantially faster. This means ViT can deliver results in real time, enhancing applications such as medical imaging, vehicle safety, and robotics. What's even more remarkable, as reported in several studies, is that ViTs and their self-attention mechanisms tend to perform more effectively for complicated visual tasks such as those which have low texture information, small regions of interest, and complicated patterns, whereas CNNs tend to overfit in the presence of noise. This is one of the areas where vision transformers shine particularly brightly. Let's take a moment and appreciate how impressive and significant these advancements really are. Now, let's take a look at how these incredible improvements are impacting real-world applications. ViTs are revolutionizing various sectors, from medical imaging to autonomous driving and beyond. In the realm of medical imaging, vision transformers are enhancing diagnostics and prognosis by identifying subtle patterns and anomalies in CT scans, X-rays, and MRIs. They're even aiding in analyzing complex 3D data from various scans, as opposed to relying on conventional CNNs to provide improved accuracy and efficiency. In autonomous driving, imagine a vehicle that can instantly and accurately identify pedestrians, cyclists, and other vehicles in varied conditions, even with poor visibility. ViTs are paving the way for such self-driving capabilities by providing superior object detection and scene understanding. Meanwhile, in robotics, these models are powering advanced robots, enabling them to see and adapt to their environment more effectively. Think of surgical robots, construction drones, and robots that can perform assembly tasks. Consider how the world's greatest manufacturing facilities will transform due to these technological innovations. These few examples illustrate how much the world is changing thanks to vision transformers. These are truly game-changing improvements, and this progress is just beginning. More advancements are to be expected in future years, leading to wider implications. Now, let's shift our focus to another fascinating development that's closely related to vision transformers, helping to address some of its inherent shortcomings: Masked Autoencoders, or MAs. Now, you already know that pre-training vision transformer MAs offer a clever solution. Instead of using labeled data, they rely on self-supervised learning. This ingenious approach uses an encoder and a decoder as an autoencoder. In other words, the model takes an image as input, masks out random segments or patches of the image, ignores these patches when feeding it toward the encoder of the model, and then tasks the model with reconstructing these masked segments. Essentially, it forces the model to learn effective representations of visual data without any explicit supervision as to the actual content of the image, such as its class labels. This technique leverages the intrinsic redundancy present in images to obtain high-quality reconstructed images. The remarkable success of this approach lies in its ability to achieve significant performance gains without requiring extensive, annotated datasets. This opens new pathways for the optimization of training, especially for small or medium data sizes where traditional supervised approaches struggle. Furthermore, it also offers a promising direction to boost training efficiency for various vision tasks. Many deep learning models, such as ViTs, commonly rely on pre-training on extremely large datasets like ImageNet for achieving SOTA results. This is not just a problem for academic researchers. If a company needs to build and train a vision transformer model for a specific domain, acquiring and labeling the dataset for pre-training is likely to be costly and time-consuming. Therefore, a technique such as MAEs is very useful. The impact of MAEs extends beyond simply streamlining training processes and reducing training data needs. MAE models are actually improving the model's generalization capabilities. The resulting model performs well on tasks and datasets that differ from the data used during pre-training. Let's dive into how MAEs work, including what are the architectures and training setups. The MAE architecture, as you probably have now guessed, involves an encoder and a decoder which jointly function as an autoencoder. It takes an image, masks some percentage of its patches randomly, usually around 75%, forwards the remaining parts, visible patches only, through the encoder, and then reconstructs the masked patches through the decoder. This is unlike the vision transformer architecture, which takes all patches across its encoder. The encoder, in most implementations, is a vision transformer. Therefore, what we have here is simply a ViT encoder followed by ViT decoder. A key to the success of this approach is to use a lightweight decoder, typically with relatively few layers that only attend to the masked tokens, as well as the output of the encoder to predict the missing token maps. A simple mean-squared error loss is often then utilized comparing the original and predicted patch representations. This simple approach results in a model capable of predicting the masked region's representations while only relying on the encoded information from the other, visible, patches, allowing for efficient training and effective utilization of computational resources. Furthermore, this configuration introduces additional learning and generalization capabilities. During training, the model learns to find and highlight the most critical regions in an image, while simultaneously recovering even fine textures along regions that have high variance. It also learns how to extract relevant information efficiently, thereby improving its capability to maintain performance under noise and small or medium data sizes. In their experiments, the authors found that this simple yet effective approach had several benefits. Firstly, masking a high portion of random patches is effective at improving performance without any increase in computational cost. Secondly, it outperformed training the model with supervised learning when the data sizes were sufficiently large. Lastly, it displayed a clear scaling law, with its performance improving consistently with increasing model sizes and training data size. The authors claim that their model performed similar to the one trained supervisedly with 10% of data and computational resources, and even slightly outperformed the standard ViT when the number of images was close to 30 million. Let's look at some of the challenges and opportunities brought about by this technique to further improve our machine learning skill set. While MAEs offer incredible pathways for accelerating the training of vision transformers and reducing the need for costly large datasets to pre-training, there are still a few hurdles we need to examine. For one, while the model performed well in their initial tests on natural images, it is not entirely clear how well it can work with less commonly used images such as medical or satellite data. Although the authors noted that the model's ability to recognize important information from noisy images suggests potential applications outside natural images, it is still necessary to investigate performance on these types of data, especially when this technique is applied to various visual tasks. Also, while the masking strategy works well in their experiments with various levels of masking, it is important to find an optimal value for the level of masking that works best given the dataset and the task that is to be accomplished for each class. This is important especially when performing fine-tuning with limited amounts of data and when the images have low texture or a low level of variance. There are some significant improvements still to be made. The main challenge is maintaining performance in the presence of domain shifts, meaning that the model should perform well on data that differ substantially from what the model has been trained on. Also, despite the introduction of various tools to enhance the interpretability of these MAs, it is still not entirely straightforward to understand how these models are making predictions. As such, even though the models are performing well, it is necessary to investigate these models even further to understand how to make them more interpretable. It is important not only from the perspective of model improvement, but also to ensure trust in the process of using these models. It would be also interesting to see if a similar strategy could be used on other data modalities like audio, text, or video as well. It was found that, even with a reasonably large pre-training dataset, and despite improvements in the model's performance, MA models still did not match the performance of models trained supervisedly, and researchers are continuing to work on this. Despite these limitations, MAs have the potential both improve and drastically accelerate the development of vision transformer models. This makes the technology useful for industry, research, and any field that works on creating models for image processing. Now, let's switch gears and examine how developments in vision transformers and masked autoencoders are impacting the deployment of AI solutions in constrained environments such as edge devices. You've already seen how much these models benefit from large-scale pre-training. However, running these large models on smaller devices presents considerable challenges, particularly in terms of memory and computational resources. Edge devices tend to be constrained in terms of both available memory and processing speed, but many AI applications such as robotics, automobile vision, and security cameras require on-device decision-making. If an autonomous vehicle needs to stop before hitting an object, it must rely on processing that's completed on the edge without a wait for communications with cloud systems. Similarly, if a robot surgeon needs to implement corrections during a surgery, it requires an immediate decision, as delaying it even for a small fraction of a second can introduce risks and potentially life-threatening consequences. A key to successfully deploying such large models is to make them lighter. This often involves retraining the models with the aim of having a smaller size without introducing more errors, which is not always straightforward. Techniques such as knowledge distillation and model pruning are often employed to reduce model size without sacrificing performance significantly. Although these optimizations, implemented in software, require a degree of engineering finesse to achieve good results for each specific task, application, and datasets, advanced tools are becoming available both in research and commercially that enable researchers to build such smaller and efficient models while still maintaining performance. To make these models particularly suitable for edge devices, it's important to consider specific optimizations targeting compute, memory access, and power utilization. New hardware designs tailored towards these models can also assist greatly. Such chips implement dedicated processing units and memory controllers to efficiently handle the tensor operations that are specific to these models. Custom hardware implementation combined with architectural optimizations makes it feasible to run even large-scale ViTs and MAs on small devices, enabling the application of cutting-edge AI techniques in a wider range of deployment scenarios and to many diverse technological applications. What's more interesting is that such small, efficient models may have benefits for larger, non-edge deployments as well, due to reduced compute requirements and faster training times. We'll explore a few examples of ongoing work and the exciting opportunities arising from these ongoing initiatives. OpenAI has recently introduced Sora, a groundbreaking text-to-video generative AI model that produces high-quality video clips based on natural language descriptions. Generating realistic videos and animations from text prompts represents a remarkable feat in AI, and this technology has the potential to transform how we create and engage with visual content. The technology behind Sora opens new avenues for research and applications in various domains. It is worth noting that Sora's architecture is based on the diffusion transformer, DIT, which employs a transformer to transform noisy image data into a form that is closer to actual images or videos. The adoption of this architecture enables Sora to perform highly efficient image and video generation, particularly in generating high-resolution, high-fidelity video clips, surpassing the capabilities of traditional diffusion models. Sora's capacity to operate at variable durations, resolutions, and aspect ratios reflects its versatility in handling varied visual generation demands. This adaptability allows generation of videos perfectly suited to specific devices and applications. Furthermore, the ability to utilize images or videos as prompts in addition to text expands its capabilities into animation and prediction tasks. By combining and fusing existing images or videos with text prompts, Sora demonstrates exceptional capability in creating realistic and seamless video content that extends existing video, creating a new video that might represent the past of the provided video or its future. Sora's performance marks it as a compelling example of how technological advancements and machine learning research can help us create cutting-edge technologies, transforming the way we create visuals. The ability of Sora to consistently synthesize 3D, consistent elements across complex scenes showcases the immense potential of diffusion models in understanding and representing spatiotemporal dynamic relationships and details. It's a glimpse into what AI systems might achieve in future years by further extending these capabilities. I hope you guys enjoyed this dive into vision transformers and masked autoencoders, and I sincerely appreciate you taking the time to watch this video. We started by investigating the fundamental principles of ViTs, then moved on to discuss the innovative concepts behind MAs and how they're complementing ViTs. Finally, we addressed the challenges and opportunities in deploying these massive models for edge devices, exploring how advancements in hardware and software are enabling the deployment of increasingly large AI models. We also reviewed Sora as a particularly compelling instance of what large models can achieve in the near future. From medical scans to self-driving vehicles to robotic surgery, the practical implications of these technologies are truly transformative. Remember, this is just the tip of the iceberg. The development of AI is accelerating at an astonishing rate, with new breakthroughs consistently appearing. So keep your eyes open, stay curious, and keep learning. There's a whole exciting new world out there. Make sure to subscribe to All About AI Tech for more exciting explorations into the future of artificial intelligence, and don't forget to share this video with your friends and colleagues who may find it interesting. I also really appreciate any feedback, comments, or ideas for our future videos. I wish you guys a super successful week. Until next time.